Hello, my name is Brian Palacios, and I will be going over the Cantor Set today. So, before anything, I have a question, or better yet, I have a riddle that I want to ask y'all and see if y'all can figure out. So, what is it? What gets bigger when more is taken away? Well, before we fill this hole and figure it out, let's get into my project. So here's my outline. We're gonna go over the Cantor set, the history, construction, the tools we're using to measure, the lengths of it, basically how it's uncountable, some applications, and at the end my conclusion and references. I make sure to fill in every hole there, so we could to make sure it's very well explained for y'all. All right, let's begin. So what is the Cantor set? So let's take a line segment from 0 to 1, basically, okay? And what we're going to do is we're going to split that line into thirds, and we'll remove the middle section, okay? And then with those smaller pieces, we'll also break those into thirds and remove the middle section. And so that's all we're doing, is taking each new segment, breaking it into thirds. And I'll show you a picture so we could actually visualize it and see it better. But the Cantor set was first introduced by German mathematician George Cantor in 1833. So who made it? So if you've been paying attention, it's George Cantor again, and he was born on March 3rd, 1845, and he was born in Russia, but at an early age his family moved to Germany because of his father had an illness. He studied and got his PhD at the University of Berlin, and George Cantor really thought about and contemplated infinity. And more so, are there different types of infinity? Is there just one infinity? Are there infinities that are bigger than other infinities? And George Cantor really thought about this. And the Cantor set is definitely part of this infinity thought process. So why is the Cantor set interesting? The Cantor set is interesting because we have a line and we keep on removing parts of it, and we keep those endpoints, which this Cantor does, and we keep those endpoints, and those are our numbers that are part of the Cantor set. So the more we remove, it has a length of 0. We basically remove the whole line segment, but it has an infinite amount of points that are in this 0 length line segment. And not only does it have an infinite amount of points, but it has so many points that it's as big as the set of all real numbers, which is paradoxical in a way because we keep on removing, but we're making a bigger and bigger hole. We keep on taking stuff out, but it's still as big as the other set of all real numbers, which is very interesting. So let's see its construction, right? We say we take a line segment from 0 to 1. Line has a length of 1. And we split it and we remove the middle third part. So right here we remove a third, and then we remove this right here. So we're left with these 2 line segments, which are a third also at lengths. So these endpoints right here are in our set. And then we do the same thing, and these endpoints are in our set. And we keep on doing this an infinite amount of times. Okay? So I can read your mind. And I know what you're thinking. You're thinking, what is the answer to that riddle? And, well, before we get to that, I still got some holes I gotta fill in and make sure I get covered here in my project. So let's keep on talking about the Cantor set and keep on going, and we'll get back to that. So here are some tools we'll be using to show some proofs, minor proofs, just to show how the lengths of the Cantor set and how it's dense and how it has as many numbers as the real numbers. Okay, so let's see. We have the measurement of the Cantor set is 0, right? 0, like one big hole. That's what it is. Okay, so how do we prove that? So let's take what we know. Let's take how we construct the Cantor set. So we have our line segment, which is 1, right, from our previous illustration. And we remove a third, correct? So we have 1 minus a third, and we could add it up there, and it would be 2/3, right? And then we remove the middle thirds of those third line segments, and so we remove actually 2 sections of a ninth. And so we could keep on doing this, and we end up getting something like this, but that will go all the way to infinity. So what I want to know is these numbers right here, what they sum up to, right? And we could actually rewrite these numbers as an infinite series, as I'll show down below. So I want to add them up, like I said, and I've done the mathematics for you, so don't worry about it. You do not need to figure it out. But what happens is we find out that everything's being is being multiplied by a factor of 1/3, and also that this part right here is just being to a power, is 2/3 to a power. So it's going to be 2/3 to a power and multiplied by 1/3. And this is called a geometric series. And so we write this infinite summation as this, which is a plus ar squared, which we have here. In this geometric series, we actually could figure out the lengths of it by using this right here, which is equals to a, which is our 1/3, divided by 1 minus r, which is our 2/3. So when we plug in our numbers, we get this. We get our infinite series actually it all sums to 1. So we're going to take our 1 that we had here in the beginning, and then we found out the sum of these numbers. So, and that's 1. So therefore, it will be 1 minus 1, which is equal to 0. So it has a length of 0. But like we said, the Cantor set is just one huge hole, pretty much. But it's uncountable, so it has infinitely many numbers. And uncountable means, too, that it's one of the bigger infinities, like we said. Because it's bigger than the set of natural numbers. But it is also as big as the set of real numbers. Which, the more we take away, right? And you think it wouldn't be so big, but it is dense in that area. So let's see. How did Cantor prove this, or what was one proof? Because I know he did about 2 proofs of this. But one proof is through the diagonalization method, and that's where first we could every point on the Cantor set, we could actually identify through location. So it could be one point would be go to the left, then go to the right, and then go to the right again, and then go to the left. Or another point is left, 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 left. So 0 would just be left. So we could actually write the Cantor set, the numbers in it, just in as from 0 to using 0 and 1, which is 0 would be left, 1 would be right. And that could actually, it could be a guidance system to get to certain numbers. So we could write our numbers as an infinite series of zeros and ones. So I won't show you with zeros and ones, but I'll show you with actually just these infinite numbers right here. How Cantor says the numbers in the Cantor set are more than the numbers in the natural numbers. So the natural numbers are from 0 to infinity. But Cantor says I could take any number here and take the diagonal, right? And I will take them and then I'll add one digit to it. And that means I've created a new number that is not in the set that we have. Therefore, that this infinity that we're using, the Cantor set infinity, is actually outgrowing or beating the natural numbers infinity by, not by 1, but it's always being bigger than it. That's how we know that the Cantor set is uncountable through this method. And so one might ask, what are the applications of this? And so the Cantor set is used in many branches of mathematics, such as real analysis, topology, fractal geometry, measure theory, and dynamical systems. If you've ever seen the Avengers, you've seen where Tony Stark is working on the Mobius strip. So I'm sure Tony Stark, that's whenever they were trying to go back in time. So I'm sure Tony Stark knew quite a bit about the Cantor set and needed it to prove some theorems to be able to travel back in time. So it's used for higher level mathematics, but it does find its way into the real world somehow. And so what about the real world? And let's think about the set. And it's infinitely dense. It's dense. It has more numbers than the natural numbers. So let's think about probability in a way, and it kind of relates to the real world. And what's the probability of hitting a certain point on a dartboard? And that probability would be 0, because it'd be impossible to hit just a certain point that I tell you to hit on a dartboard. And so when we think about that, if we add up all those probabilities to hit certain points, then the probability to hit the dartboard itself would be 0. But we know that we can hit the dartboard with a dart. So we're using our natural numbers, it would be impossible. But in a way, we're showing in the Cantor set that there are more real numbers, or more transcendental numbers, as they would call them, than there are actually just numbers in general. And so that actually gives us probability and actually says, okay, it's not actually 0. There's actually a certain probability of hitting the dartboard. And so that's one way the Cantor set actually makes its way into the real world. So I think I've covered all my plot holes in here. And so let's get back to the real question, right? Which is the conclusion. So the Cantor set again is, I had to see one thing I didn't cover, but it's dense, it has 0 lengths, it's uncountable, it's paradox, it's something simple, but very complex in a way, and it's mathematics. So now let's get to it, right? The riddle. So what is the answer to the riddle? What gets bigger when more is taken away? And the answer is, well, a regular person might say a whole, but a mathematician might or would probably say the Cantor set. Thank you. My name's Brian Palacios.